Like you haven't heard this yet. So I'm Gordon, our facilitator is Florian. So today the paper we're going to be going over is Unsupervised Data Augmentation. The primary author, Chi-J Xie, and several other co-authors from Google Brain and Carnegie Mellon. This is what we're going to go over. Motivation. So deep learning is, typically requires a lot of labeled data in order to succeed, and labeled data is very expensive. So that's one of the main motivations for this paper. Some of the less costly ways of applying or improving deep learning are using unlabeled data, which is much more abundant and easy, cheaper to accumulate, and data augmentation, which basically stretches your supervised labeled samples further. And as well, are we good with the sound? Data augmentation has mostly been applied in the supervised setting, and so we want to see if it can be applied in the unsupervised setting as well. The main contributions, which we'll get into, are applying state-of-the-art data augmentation to semi-supervised learning, a training technique called TSA, training signal annealing, that effectively prevents overfitting when you have much more unsupervised data than supervised data, and they achieve performance improvements on multiple text and vision benchmarks. And then they also introduce a method to even the prediction distributions over across classes for unlabeled and labeled data. Semi-supervised learning. I hope people online know what this is. I probably won't explain it again. So we'll get into smoothness enforcing. Okay, so this is one approach to semi-supervised learning. And the general idea here is you try and regularize a model's prediction to be less sensitive to small perturbations applied to the input data. So that input data can be labeled or unlabeled. And when we say perturbations, we're basically talking about adding some sort of noise to the input samples. And so yeah, you want your model to, given a sample and an augmented sample or a perturbed sample, you want the model's predictions to be similar on both. I think that's what I just said. So enforce the predictions to be similar. And in general, you want a good model should be invariant to small perturbations on this input data that don't actually change the nature of the example. And yeah. So data augmentation is a technique to boost your training data size and the diversity of it. So the general idea is you're augmenting in some way, again, adding some noise to your input samples so that you can both get more training data and have more diverse training data. And I guess we'll see some examples of what diversity means. So yeah, basically you apply some sort of transformation. You have a transformation function that you apply to your input data. And in data augmentation, there's always this trade-off of diversity and validity that's being managed. So yeah, you want to create novel and realistic training samples without augmenting them so much that you change their underlying inherent label. So diversity means growing the reach of your data set or making your data set more broad. And validity is making sure that you're not blowing up your samples so much that they are no longer recognizable or they're not related to the label that they should have assigned. Any questions so far? Okay. So this is what supervised data augmentation looks like here. So here Q is our transformation function. So you can see it's conditioned on an input example X, and then X hat is the augmented data sample. And so basically we're trying to minimize the log likelihood, the negative log likelihood of the true ground truth label, which is Y star, given an augmented sample X hat. And so yeah, you can see this as basically an additional training signal that's being sent to the objective function that is hoping to, yeah, that is just using the augmented samples. And then very similarly, or actually slightly differently, unsupervised data augmentation. So this is when you have unsupervised, unlabeled data. This is a common way to use that data for data augmentation. You can basically take, examine the output distribution, prediction probability distributions for an unlabeled sample. So here that's X. And then an augmented unlabeled sample, X hat again. And you've got the same transformation function Q that you had in the supervised setting. And so really what you're trying to do is, in this case, minimize the divergence or the difference between these two probability distributions. So you're trying to normalize or regularize the predictions on the augmented samples to have similar class distributions to the unaugmented, unlabeled data. Does anyone have any questions here?
Can you go back to the previous slide? So, doesn't minimizing this minimize the other one as well?
Minimize this, minimize the other. In this case, oh sorry, maybe I misspoke earlier. In this case, these are, X is all labeled, labeled samples here.
In the other one, what are the Y's there?
The Y is, so Y here is not the ground truth label.
Okay. Okay.
Y here, so this is Y star, that's the ground truth annotated label. And here we just have the output prediction distribution from the model for both the unlabeled and the augmented unlabeled sample. Yeah. Jake?
What's the difference between the theta and theta tilde?
Oh yeah, good question. So theta is implying that these are parameters that are being updated. So the gradient is passing through these. I'm pretty sure that the idea with theta tilde is those parameters are frozen. So they're not updated in the objective function.
And is theta the same model parameters as the labeled data set from the slide before, or are they different?
Theta here?
Yeah.
Yeah, so this
the same set of theta.
Yeah, these are two different settings, but yeah, in both cases they're the model parameters. Does that answer the question?
What is Q? Its distribution.
Q is the transformation function, so the augmentation function, basically the way that you're adjusting your input samples.
So here, the first term in the KL divergence is X is the actual, the data that you have labels for.
In this one?
Yeah.
So in this case, the unsupervised data augmentation, you're assuming that you have, so yeah, I guess you can see here, you've got X in U, okay. And U is an unlabeled set, whereas in the first one, you have X and Y star in a labeled set. So yeah, there's no labels in this data at all. So this actual approach, there are a few different ways you can do this. This specific approach of using the KL divergence between the the augmented and unaugmented was from a paper in 2018, VAT, I believe was the model. So they borrowed that approach here. And really the main difference they applied in this case is the transformation function, so what they did with Q. And so that's what we're going to talk about now. So this idea of targeted data augmentation. So over conventional methods such as adding Gaussian noise or affine transformations, perturbations like that, there are a few advantages of applying targeted augmentation. So one is that they give a valid and realistic perturbation. So the idea is when you apply some of these state-of-the-art data augmentation methods, the output augmented example is still very much in the same distribution as the sample it was transformed from. So these are sort of realistic augmented examples. Whereas when you just apply some random Gaussian noise, it can often make the data point, if you apply too much, make it sort of very unrecognizable and not realistic, so not really, as we say, valid. It also applies a diverse perturbation. So again, if you want to use those other methods, such as adding Gaussian noise, you're usually not going to change or you're not going to be able to change your input samples significantly enough. And so you just end up with sort of local changes to the samples. Whereas with targeted augmentation, you can really generate diverse samples that are much more useful in growing your training set. And then as well, we'll see with some of the methods, they had a targeted inductive bias. So yeah, you can actually apply approaches that are optimized for the task that you're solving in the particular data set. And so we'll see an example of that in the augmentation strategies they applied.
Was there a question back there?
Question? No? So this is the training setup that they applied. So on the left-hand side, we have the labeled data, and it's split up to X and Y star. Pardon me. X is fed in through M, that's the model. And then we just have the standard supervised cross-entropy loss being calculated here. That's feeding up into a final loss. On the right-hand side is where they take the unlabeled data, and they do two things. So one, they feed it through the same model, and then as well, they take that sample, the unlabeled sample, and then they apply some augmentation to it. So we'll get into all these different augmentation strategies. So that results in X hat. So this would be their Q, their transformation function. So they get X hat, and then they feed that through the model as well. And then they take the output of the model on X and on X hat, and they feed that into the unsupervised loss function. And that's the KL divergence that we saw here. So basically, they just take a weighted sum of the supervised and unsupervised loss and combine those together. Question?
Yeah, what is supervised cross-entropy loss?
This is just the standard loss function for across the, so you take the ground truth label and compare that to the output prediction probabilities.
Okay, thanks.
Yeah, Joey.
So none of these data seem to have the tilde over it. Does that mean that?
Oh yeah, that's a great point. I'm pretty sure they forgot to apply a theta on this, this prediction distribution. So the idea is when the gradient propagates back through the model, it will run through the supervised portion, and it will also run through the augmented application up here. But I'm pretty sure it's not flowing through just the unaugmented, unlabeled data.
So why is that?
Good question. I can't remember if there was a justification for that.
It's in the other DOT paper.
What's that?
I think it's, yeah, they just referred to the other paper.
And okay.
Where in this flow does the targeted or the diversity augmentation, where does that come into play in this flow?
The targeted? Okay, so the idea is that based on the type of input data that you have for the unlabeled data, they'll apply a specific augmentation to that sample. So here they've listed the ones that they've used, but the idea is they only use one at a time. So based on the type of data you're using and the particular data set, they'll apply a particular augmentation strategy. So I think in the next slides it'll show the particular policies. They just sort of listed them all here.
On the left-hand side is the labeled data. So you have the ground truth, the Y star. The right-hand one, you don't have one, right? So the left-hand side is you're doing the prediction, training, and the right-hand side you do the prediction, inferring. Is that?
Yeah. So on the right side, yeah, the loss function does look different than on the left, but in both cases you have a version of the model and with its parameters that can be updated with signal from the loss function. So in the unsupervised case, this is the function that is leading to the unsupervised or signal flowing through the unsupervised portion. Yeah. So there's just two different loss functions. One looks like this, and then the other is just the standard.
Question.
Online?
Online, yes.
Okay.
Scheduling of training, do they train all supervised first, then unlabeled? Or are they training all mixed together?
That's a great question, and that relates to the contribution that I mentioned earlier, TSA, the training signal annealing. So we'll probably wait until that to explain that.
Yeah, so for the unsupervised side, it doesn't matter what the label, what the model, what the label assigned by the model is, right? Like the loss doesn't.
Yeah, really all you care about here is that the amount that you're changing your sample by is not differing significantly from the same model prediction on the model prediction on the same unlabeled sample. Okay. So going into the augmentation strategies, the first one I'll talk about is AutoAugment. So AutoAugment, learning augmentation strategies from data. The general idea here is they have input data on the left, and they basically have a model that will automatically search through multiple different augmentation strategies. So you can see here in policy 1, they're making a transformation, a rotation to the input data. The other ones are mostly changing the color of the samples. And so the idea is the model will automatically select the policy that is adding the most novel signal to the training. So for example, if and they find that in different data sets, different policies are optimal. So in one data set, you might need to modify the color of your images a lot to get more diversity and improve your training set. And in another, you might need to rotate the images, et cetera. So basically, it's again, coming back to the idea of being a targeted policy. This is something that you can vary on a task-by-task basis. So even on a particular data set, you can see what's the optimal augmentation approach. Any questions on this one? So that was the one that they applied for vision, and then they have two for text. One is back translation. So the general idea here, it's pretty intuitive. You take a question in one language. In their case, they used English to French. So they trained a machine translation model between those two languages. Then they translate the English sentence into French. They then take that French translation from the model, and they translate that back into English. And then they use that as the augmented sample in the model. So obviously, any machine translation model is going to have some loss, and it's not going to exactly translate something the same way back and forth. So in this case, you can see a lot of it has stayed the same. This is Google Translate, but this word crankily was previously gringingly, and I think spoof spoof gets translated to travesty. So this is one way that you can augment your samples. And then the other one that they have for text is this TF-IDF-based word replacement, and they use this for text classification. So the idea here is sometimes in back translation, the augmented transformation might actually mistranslate some of the key words for that sample in the classification task. And so here, they basically assign an IDF score to each word in the sample, and then they randomly sample or randomly swap out words, and giving a higher likelihood to swap words that have a low IDF score. So here you can see I've just sort of created this example. And so in this case, the words this, in, decides, to, etc. are transformed or swapped. But the words that are a little bit more rare and therefore have a higher IDF score, such as pathetically, cringingly, spoof, those are more likely not to be swapped out. And so that's, yeah, based on the intuition that certain keywords sometimes are really useful for text classification. Any questions on the strategies? Those are the three. Okay, so now we come back to the question of how do we balance the need for having a large model? So when we're dealing with unlabeled data, of which we have a really, often you have much higher volume. You have much more unlabeled data than say, labeled data. And so you generally would need a very large model to train on that data. So, but you may have a small amount of labeled data. So the question is how to balance the need for a large model while preventing overfitting at the same time. And so their answer to that question is to gradually release the training signals of supervised examples as the model is trained on more and more of the unsupervised examples. So I'll show the equations for all this. Okay, so here, let's see. So B here is the batch. Z is just a renormalization constant. And the key is this part over here. So again, this is the objective function. And so really what they've introduced is this portion on the right-hand side where they say, and this is all with regards to the labeled samples. So N, or what's this constant again? Eta? Eta? Yeah, so eta of t is a threshold that varies with your training progress. So we'll see that in the next slide. But basically it's a threshold. And if the model's prediction probability on the correct class for a labeled sample is above that threshold, then that this will evaluate to 0, and therefore that sample's signal will not get propagated through to the loss function at that time. And yeah, so the constant will change over time, but generally the idea here is that when when eta is small, then you'll pretty much be rejecting most signal from labeled samples from going to the loss function. So you'll be preventing the model from overfitting on say a small set of labeled data. So that was the reason they introduced this. Any questions?
Question, yeah, is I the indicator function?
Yeah, sorry, I didn't say that. I is the indicator function here. And Z is just to rebalance or renormalize the effect from that.
Does eta go from high to low or low to high during the training?
Eta goes from, it's always increasing.
Okay.
So I'll show the schedule. So they introduce a few different schedules for ADA. So here's the equation for ADA on the right. K is the number of classes in the classification example, and lambda of t you can see in the plot. So lambda of t varies with the training progress, and as lambda of t increases, or sorry, as training progress increases, lambda increases, and as well the threshold also increases. So at the beginning, lambda will be 0, and eta will be 1 over k. So 1 over k is 1 over the number of classes, which is just the random chance of predicting a sample. And then at the end, eta will be 1. And so coming back to this equation, if eta is 1, that means every single sample practically will be carried forward towards the loss function. And at the beginning, when it's 1 over k, only the samples that the model is very unconfident on will actually be used in the loss function. And so the idea here, the intuition is that if you have a small labeled set, so you have only a few examples that have labels, you want to avoid your model overfitting on those at the beginning of the training. So they suggest using this exponential schedule for the case where you have a low number of labeled examples. And so, yeah, the idea is at the beginning, you won't be feeding as much signal from those samples to your loss function, but by the end, you can start releasing more and more of it once more of the unlabeled data has been incorporated. And then conversely, if you have, say, a large number of labeled samples, then you can use a log schedule, the green line here. And so that will release a lot of the supervised signal at the beginning and less at the end. Any questions on this? I think that's it before the break. So we'll just take a 5-minute break, and then afterwards we'll go over the results and have some discussion. Welcome back to people online. The sound is working.
Okay, good call, good call. Let me just make sure.
Sound is good? Okay, great. So we're going to do a 5-minute break. No, we just did a 5-minute break. We're going to do experiments. So basically, they applied this method to 2 different types of tasks, text classification, and then image recognition, so a couple of vision benchmarks. These are the actual data sets that they used. So there's a mixture of binary and 5-class text classification. Most of it is sentiment, except for dbpedia, which is, I believe, categories. And I think dbpedia actually has 14 classes or 10 classes. The 2 image benchmarks both have 10 classes. They also use ImageNet. They test on ImageNet, and they do some ablation studies for TSA and for the targeted augmentation. So for text classification and the settings for the labeled data, so the goal here was to use a small number of labeled samples. So for binary classification, that means just 20 labeled samples, and the rest of the data coming from the unlabeled. And for the 5-class classification, they found they needed to use a bit more. So here they used 2,500 total samples, and so that's 500 per class. So in speaking to the author, the goal here was to find out how low could they go. So I was asking him, did you experiment, or how did you stumble across these numbers? And really they wanted to determine how few examples they could, labeled examples they could keep while still achieving really strong results. From the unlabeled data for IMDb, which is one of the binary classification, they used the concatenation of the training set that they didn't use. So the training data that was not used for as supervised, they used that as unlabeled, and then they used the rest of the unlabeled set. So I believe the total training set is 25,000, and the unlabeled set is about 50,000. So that's how much unlabeled data they're using there. And for Yelp and Amazon, they obtained some really large review data sets. And I believe there were something like 6 million samples in the unlabeled. And so for the most part, again, another choice was that I think for the most part they used one augmented sample per unlabeled sample. But he said that that would be something that might be a task-specific parameter and that you could adjust. So for some tasks, for each unlabeled sample, you might want to make a couple of augmentations and use both. And as for the model, they try a few different initialization schemes. So all are working on the transformer architecture applied in BERT. So they have just a random initialization. Then they have BERT base, BERT large, and BERT large fine-tuned on the unlabeled data. The in-domain unlabeled data, so the same unlabeled data that they're using. And for each setting, they compare the performance for each of these settings with and without the unsupervised data augmentation method, UDA. So here are the results for the text benchmarks. So you can see at the top the data set name, and then below that the number of supervised examples that exist in that data set. The top two results are the pre-BERT state-of-the-art, so that's how influential BERT was. There's a before BERT and after BERT. So they report both. In some cases, BERT was better than the state-of-the-art. In other cases, I guess it's always better. Okay, and then their results, the results from their paper are in the bottom in the semi-supervised setting. Again, they've got the different initialization strategies on the left, and the UDA X or check indicates whether or not they use UDA. And so these are error rates here, so lower is better. And below the data set name in the bottom, you can see the number of labeled samples that they used. So for IMDb, they literally only use 20 examples. And when they apply, when they use an initialization from fine-tuned BERT model, they're able to beat the state-of-the-art and the pre-BERT state-of-the-art. So that literally means they're just using 20 labeled examples along with BERT, which is fine-tuned on unlabeled data, and then they use augmented samples from the unlabeled data set. So that's one of the most significant improvements. And they found across the board they got very close, or actually beat the state-of-the-art for these tasks. I think the one that they found the most difficult and they performed the worst on was the 5-class classification for both Yelp and Amazon. You can see that their results are still a bit off from the baselines. So yeah, a really big finding here is that obviously just with using BERT and no UDA, you still get 6.5 error with just 20 labeled examples. So a lot of this is just indicating how much information is being contained in BERT. But it's quite significant that this shows that you can use pre-trained language models along with UDA. So it can be complementary to pre-trained language models.
So the numbers when you don't have the UDA as a without data augmentation at all, just on the 20 labeled samples, or?
Yeah, that's right. On the 20 labeled samples plus fine-tuning for the last case, but yeah, that's it. What's that?
I mean, like it's a bit unfair when you don't add any augmentation at all, just 20 labeled samples and that's it.
Yeah, they do some studies on the vision benchmarks that investigate whether or not the whether or not doing augmentation on the unlabeled data is actually more advantageous than doing it on the labeled data. So, but I don't think they did that for this. So yeah, that could be a good, unless I'm wrong, that could be a good feedback. They might have, I should say that they did do, so in speaking with the author, they did do other experiments that they didn't report here. And I think I might have asked about that. I just can't remember if that was something they did. But if they did, it wasn't as performant. So for the vision benchmarks, yeah, so they wanted to use the same model that was used for prior semi-supervised work. And this was the wide residual networks with depth 28 and width 2. And so, yeah, they used the same exact labeled samples that AutoAugment used to find its optimal policy. So for CFAR 10, which is a 10-way image classification task, they have 4,000 samples. And for, this is street view house numbers. That's a digit recognition data set. They used 1,000 labeled examples. And so they do 10 runs with this model and calculate the average and the standard deviation. So here are the results here. These, on the left, you see the fully supervised setting at the top. So with no augmentation. And then following that, you see different augmentation techniques that are applied to the unlabeled data. So I think for, can't remember how many samples, but there are roughly maybe 50,000 unlabeled samples for CFAR 10. Yeah, I'm not sure of the numbers right now, but I think you might remember earlier I mentioned VAT, which was the paper that they got the idea to take the KL divergence between the distribution of an unlabeled and an augmented unlabeled sample. So really what you're seeing here, so obviously they outperformed the previous state-of-the-art method. But between UDA and VAT, the only real difference is the perturbation or transformation function that they applied, since they're both using the same KL divergence technique. And so this is indicating that targeted data augmentation strategy was helpful.
Question about the number of unlabeled examples that they add to the data set. As you said, for example, for CFAR 10 it's 50,000. So is there any metric or measure that we can look up into, like in order to see like we are saturated, and why not using 100,000, right? So we would say more data better, but there's a point that we saturate the diversity of the data, or like the distribution or thing, the new thing that we are defining in our data, that we are augmenting in the data, which doesn't matter after that, right? So for example, when they chose 50,000, there's a reason for that. Is there any metric for that to see that level of,
I don't think they provide a metric. There might be a good discussion for at the end though, when we get to the discussion points. Like, so yeah, I'll keep that thought in mind. But as far as I remember, there wasn't anything provided.
The auto-augmentation will take care of?
AutoAugment? AutoAugment will find the optimal policy, but I didn't read the paper in depth. I'm not sure if it optimizes anything else, such as the number of samples. As far as I know, it's just finding the optimal policy for a particular data set, the optimal augmentation transformation. And okay, so they also performed some experiments on ImageNet. And the motivation here was the initial data sets they used all had between 2 and 10 classes. So they wanted to, and they all had a low number of supervised examples, 4,000 or less. So they wanted to use a data set that had a much higher number of classes, So a bit of a harder task and much more supervised examples, and see if this approach was still applicable or if it was really only sort of a niche improvement for smaller data sets. And then they also wanted to see if they could make use of out-of-domain unlabeled data that had different class distributions. So keep in mind, in all of the previous examples, the unlabeled data sets that they were using largely were just the actual labeled data without the labels being used. So it was very much in-domain, literally samples that have a true label. They just didn't tell the model what the label was. So they wanted to see if this would be applicable if you didn't have, if your label is coming from out of domain. And so ImageNet overall has almost 1.3 million images and about 1,000 different classes. So the settings, they do a couple of settings. So one is, they call ImageNet 10%. And this is where they take roughly 10% of all ImageNet data and use that as labeled samples. And they use all of the rest of ImageNet as unlabeled data. So 10% would be, I guess, 130,000 samples. And then they would have over 1 million unlabeled, or about 1 million. Over 1 million, yeah. And then the other one is the fully supervised scenario. So this is where they use the entire ImageNet data as supervised data. And they obtain extra unlabeled data from a data set called JFT. It's another image, I believe it was an automatically generated image data set. So they essentially train a model on ImageNet, and they use that model to source out the most relevant samples from the JFT data set for each class in ImageNet. So they basically, for each class, they take the, I think it was 1,300 most relevant examples from JFT, and they use that as the unlabeled set for their experiment. Any questions? Okay. The baseline model that they used was ResNet 50 here. So they did encounter some errors, some issues with ImageNet. So they observed that they had flat class distributions. So the prediction probability distributions across classes was pretty flat or uniform for the unlabeled and the augmented unlabeled samples. So there really wasn't much signal coming through from the unlabeled part of the training setup. And yeah, so there's probably to do with the fact that there are so many more classes, and there's also so much supervised data available here. Or actually, sorry, no, the amount of supervised data wasn't an issue. I think this was more of an issue even for the ImageNet 10%. So where they only had 10% of the training data as supervised, this was an even larger issue. So this led to the unsupervised training signal being pretty much dominated by the supervised signal. And so their solution, another one of the contributions I mentioned at the beginning, was to sharpen in a few different ways the predicted distribution produced on unlabeled samples, so that there would be basically to encourage the model to use the training signal from the unlabeled samples. So the specific techniques that they used were entropy minimization. So they added an entropy term to the overall objective to regularize the predicted distribution on the augmented examples to have a low entropy. So again, to discourage these uniform distributions of probabilities. They also did softmax temperature control. And here, this is to control the temperature of softmax when they're computing the prediction on the original example. and then confidence-based masking. So this was where they basically removed any samples that the unlabeled samples that the model was not very confident on. So all of these approaches were to try and sharpen the probability distribution on the unlabeled augmented samples.
So maybe we should use this for discussions, but like if the actual distribution of your training data, of your labeled training data is uniform, and then you try to sort of force it to take a different shape on your unlabeled data, shouldn't that hurt, or like why should that work?
So the number of samples is uniform across the classes, but here this is saying the problem was that the model's prediction probabilities across the different classes for an individual example were uniform. So the example has some category. Let's say it includes a giraffe, so that should be the true label, but the actual output prediction distribution was pretty uniform.
Okay.
So they wanted to find ways to encourage it to be sharper, to be less prone to just being.
Do they compute the KL divergence per batch, or like how do they compute it?
KL divergence per batch. No, I believe it would be calculated per sample. I'm pretty sure it would be each sample would.
Yeah, but it's kind of must be a batch-wise error. So when you look at the figure,
so they
have first the supervised error and then the unsupervised error, and then they do the backpropagation, right? Or they do it like separately, but the way I understood is do it all together. So they must calculate some kind of batch-wise KL divergence.
Okay. Yeah, so I suppose that they do. These are the results here. The left is the ImageNet 10%, again with the baseline it's ResNet 50, and the right is the fully supervised ImageNet setting. And top 1% is the model's accuracy for its first top prediction. Top 5 is its accuracy looking within the first 5 samples. And yeah, so you can see that it improved on the baselines in both cases. I guess a smaller improvement for the fully supervised setting, where they're using an additional 1.3 million samples from JFT. Yeah, over the previous AutoAugment policy. I think for ImageNet 10, was it for this one? Yeah, I think they also, so someone was asking earlier about why not use the labeled examples for augmentation for the baseline. And I think they also did run that experiment here. So they used the 10% labeled examples for augmentation. And so that, I think, got something like 58 accuracy, so still significantly below. And yeah, moving on to the ablation studies. So they did a couple. The first one is for TSA. So to determine if this training signal annealing actually made a difference. And so they did it for Yelp 5 and CFAR 10. In the Yelp case, they didn't use BERT pre-training, just to really make sure that there was all of the information was coming from the data used and not from the pre-trained distribution or language model. And yeah, so you can see in the first case where there's an X, that's where they're not using any TSA. And so you can see in both cases, applying some schedule does improve the results. And you can also see that it's slightly different for the two cases. And I think for CFAR 10, there were 4,000 examples. So that's optimal with the linear schedule. And Yelp 5 was about 2,500. And so that's one of the lower data settings that they hypothesized would be best with the exponential schedule. And then the other one was for, a question? Yeah.
So, do you think TSA works for pure supervised learning as well?
Would TSA work for pure supervised learning? That's a good question. I'm not sure. I don't think there's a clear reason that it wouldn't. It seems like you could apply it. So the idea would be that you would,
Overconfident one first and then add them later on.
yeah. So remove, yeah, I don't know if there would be as much motivation to do that when you're not incorporating additional data, but that's a good question. Maybe someone in the discussion will have some thoughts. And for the actual data augmentation policy, so they wanted to see here, did the targeted data augmentation that they applied actually make a difference? So they have the two image data sets here. And so on the left, you can see different augmentation strategies. AutoAugment was the one they actually used. And switched augment implies they took the optimal policy for one data set and applied that on the other data set. So you can see that it really does perform best when you take the optimal augmentation policy, the most targeted policy, and apply that to the data set. I think that's mostly it, just some conclusions. So in summary, they introduced a method called UDA, Unsupervised Data Augmentation, that used targeted data augmentation to generate diverse and realistic perturbations to input samples. And so this enforces the model to be smooth, the way they applied it with respect to these perturbations. They also introduced TSA, training signal annealing, and this was to prevent UDA from overfitting when a lot more unlabeled data is available compared to the amount of labeled data. And their results showed that they achieved state-of-the-art on IMDb with only 20 labeled examples, and they were able to reduce vision error rates by more than 30% in the semi-supervised setting. And they were also able to leverage unlabeled data to improve performance on ImageNet, even though it was maybe a small improvement. And so some overall findings are that data augmentation and semi-supervised learning are well-connected topics that should be explored further. And UDA plus unsupervised representation learning, in this case BERT, can complement each other and work well together. And so that's the presentation. We just have some discussion points to go over. Joey?
I have a question. Did they ever discuss what happens if you have a massive class imbalance and you want to augment the class that has way less data?
Right, someone was asking about that earlier. I don't think, no, they didn't do that. They specifically, in the case where they were using ImageNet and they were boosting from the JFT data set, they specifically took an even number of samples across all the classes from JFT. And I don't think there was any case where they had an imbalance across classes. But yeah, that would be an interesting problem to solve for sure. Okay, so Florian and the author, so Chijie had one discussion point that he wanted to pose to the audience, which was, so to some extent, this type of approach, the ability to use more unlabeled data can help to make machine learning more universally accessible because it's much more affordable to train models on unlabeled data. And so what applications do you guys think stand to benefit the most from semi-supervised learning that haven't already been tried in this paper? That's one question.
I would say definitely anything that's related to videos, or most of video related. Like a big problem is you have like a cooking video and you want to get the recipe. Use automatic machine translation to get the recipe. There are like small data sets available, and it's a very complex problem because of just how recipes are organized, right? So if you have a small training data that can really work, there are tons of unlabeled data for like videos for recipes, right? Say there's like GIF recipes or whatever, where you can get large amount of data very easily. It's just everything's unlabeled.
So video data, yeah, interesting.
Like you take a video and you just make a description of what is happening in the video, right?
Yeah, I don't know if that's been tried or not. And then I think, so as well, what are some other targeted augmentation strategies for text? So they introduced back translation and this word replacement. Or sorry, they didn't introduce those. Those have already existed, at least the first one. Are there any other strategies for text augmentation that anyone's used or think could be valuable?
Is UI regression when you're trying to compare your interface with a new interface, and you don't want to label everything in the test cycle. You want it to be unlabeled. There's a potential area.
UI.
It hasn't gained much traction because you'd have to label every part of that, and that's not enough for Agile. So if there was some way to do it unlabeled.
Oh, okay. UI data. And so part of the reason that I asked this question is I felt like the approaches for text augmentation still felt like they were maybe most useful for a text classification case, but there are many other tasks to solve in NLP, and so I think that they said back translation has been shown to be successful for other tasks, but I think that the word replacement one might not be as relevant. So I was curious if anyone had tried any others. And then Florian, I think you had a few here. So yeah, what are some other ways to automatically optimize data augmentation strategies?
The idea here is that you see they have like some kind of targeted augmentation strategy, right? But instead of having some kind of targeted augmentation strategy, just put in kind of like a neural network, right? So like kind of like a GAN, and then at the same time you optimize GAN to make the best possible kind of transformations, right? So the GAN would be optimized to help the other neural network to get the better KL divergence, right? I wouldn't know if this makes sense or it would work, because at the beginning, like if you want to have minimal KL divergence, you would just do the identity, right? So I wouldn't know, but I think it's an idea I can throw into the room.
So you mean just like a generative network?
Yeah.
Instead of using a specific target augmentation? Why not? Yeah. Let's try it.
Yeah, you can also use like some kind of variational autoencoder. Right? It doesn't need to be a GAN.
Yeah, some generative model to come up with a policy. Yeah, I think it ties in with some of the other points. So you were thinking about should we compare UDA or combine it with automatically generated data sets? This is like an active field of research as well.
Nice.
So data sets that are completely fabricated without any annotation. Is this something that competes head to head? Like are they strictly one or the other, or can they be combined? And another food for thought is, will in the long run UDA be a cost-effective alternative to cheap manual labeling? So if manual labeling is, I think you threw out a number like 140 per hour with
140 US.
US?
Yeah.
140 US per hour. will this actually be a cost alternative method if the costs are that low? Paul?
Well, I just wanted to point out maybe like one of the challenges that this type of approach would face, and that's handling data privacy. I'm not sure if there's an easy way to build in something like differential privacy or something like that in order to ensure that when we're gobbling up unlabeled data that we're not accidentally throwing in user data that might be they could be victim of like malicious attacks, right? So.
So something to keep in mind with when applying this method.
Well, if you have sorry, just want to add something. So you have your private data, right? So your neural network or your model will still look at the private data, right? You just don't have the label at the end. So if you have all the customer data, right? And you want to do some machine learning, you still have all the customer data. The neural network still looks at all the customer data. Wouldn't change much in the end, you just don't have some kind of label or decision making. So,
Question, yeah?
Oh, based on what you were saying, I think this could be used for data sets where the labels might be retroactively applied. Like you were saying, the case about like credit scores. So like maybe there's a lot of inconsistency in like the ones who retroactively got approved for credit. So like there might be the human error, inconsistency, or just like the fact that there's self-selection or something. So like this could kind of help with that as well, right? Like you were saying, there are some people who maybe fit the traits of being approved, but then they just somehow didn't get approved. So then their actual label would be not approved, right?
Yeah, if there's some bias of some sort in the labeling process, the annotation process, then definitely that could mean that the samples in your unlabeled set are valid, but just not being included for one reason or another. So I think, yeah, those kind of cases are really good candidates for this kind of work. Any other thoughts or questions?
I wonder how maybe we could apply, whether it would be an interesting case of instead of doing supervised learning, we would be doing an unsupervised sort of clustering job and using the sort of the model, the unlabeled data model to maybe, if you have to do a clustering job on a very large data set, could you actually first do a clustering job on a much smaller data set and use those as the labeled, as the sort of supervised set, and then apply this to then infer the classes of all the others and see if those classes would actually fit in the initial cluster class, and whether it would be actually faster than doing the big, massive clustering job.
Interesting.
I don't know, I'm just
okay, so
initial thoughts, but.
So the idea would be to take a subset of the unlabeled data, you have strictly unlabeled data, take a subset, train a clustering model on that, and use the clusters as ground truth labels. That sounds to me like a cool way of starting from scratch. Like you have no labels. I think that's been done before, but in conjunction with this type of approach would be interesting. Yeah. I don't see why you couldn't do it. I think you might find that I don't know how well it would perform.
Yeah, that's the thing. I don't know.
But
I wonder if there could be an improvement there or not. So we'll try.
Yeah, as opposed to just doing it all at once.
I have like one criticism about this paper. I only skimmed it and I wasn't able to follow your entire presentation, so correct me if I'm wrong. But it seemed they call it unsupervised data augmentation, but it seems that like especially in the case of text, they use the model to translate and translate back. And there's a very
It's a separate model. They train a separate machine translation model to do the back translation.
But they do utilize that model for data augmentation, right?
They use that machine translation model just to generate the augmented samples.
Yes.
Yeah.
So I guess my criticism is that they say it's unsupervised, but this is not exactly distillation, but there is some kind of, because that translation back, that's supervised. And there is a lot of like that kind of signal that's kind of being learned and distilled by doing this approach, even the TF IDF frequency approach. So there's a very strong prior that you built into the augmentation part. So this doesn't feel like it's like exactly unsupervised in the sense that you just give a lot of data, but there's some kind of implicit supervision. I don't think it's exactly distillation, but something very similar.
And I think it's acknowledged. So they call it, I mean, they're using the language of targeted data augmentation. So you're picking an augmentation strategy that is targeted to the particular task, and in some case to the data set that you're working on.
Okay.
So I think it's not an unacknowledged part of the paper.
Okay.
Like they are, it's yeah, on purpose that they're doing it that way. Nonetheless, I do agree that I don't know how well some of those, that was my question here, how some of those augmentation strategies would apply to other, for example, text tasks. So yeah, it remains to be seen how much work you would have to do to come up with an augmentation policy that is successful for a particular task and data set. I think that would probably be very interesting future work. Yeah.
Okay.
Joey.
Something to add on to that, something I think would be interesting is what happens if you have a worse back translation, because you're adding a greater perturbation to it, right? Then does your UDA become better because you have worse back translation for that?
Oh, if your machine translation model is less accurate?
Yeah, because you're creating greater perturbation, right?
Yeah, I think that comes back to that trade-off between diversity and validity. If your translation model is terrible, then the actual sample that you generate is probably not going to be a valid sample for the label that it's supposed to be assigned to. But if you don't change it enough, then you're not really adding any new signal. So yeah, there's some inherent trade-off there, I think. So yeah, maybe using a slightly worse translation model would be effective. Definitely not using a terrible one. But yeah, it's a good point.
Yeah, I'm wondering the other scenario, and that's some kind of the scenarios image segmentation. So that means they had like the to extract the different level of the target from the background. So in that scenario, how can we use the UDA to data augmentation?
When you have different, so this is for image segmentation?
Yeah.
Or object detection, or?
Yeah, because this scenario is one output layer for the final, but the other, some kind of the neural network of the model, at the end is the output should be the images.
Sorry, at the end, the output of the augmentation?
Yeah.
Right, so that's a good question. I'm not too sure. I'm sure there's been work done on augmentation for object detection and segmentation, but I'm not too familiar with that work. Yeah, so I don't know exactly how it's applied in those settings. Is that the question?
Yeah, because it's a heavy work for you level the tree there, the card there.
Yeah.
Yeah, but for this one, you it's a prepare the distribution of the Y and something else. But if in the segmentation, and how we prepare the.
I mean, I think you can still, some augmentations are pretty clearly still valid. If you just change the color, for example, the object detection is still going to be valid. You're not transforming or rotating or moving anything outside of a box. So I think that's one approach you could take. And I think color augmentation was one of the strategies that they used for the image data sets. So maybe we'll cap it there. Thanks very much for your attention. There's some appendix, that's all. And that's it. Thanks, guys.